Combinations of random variables. We have several formulas that help us to better understand, help us to better describe normal distributions whenever we have different random variables and we combine them by addition or subtraction. Or when we have the same group, the same random variable happening in sequence, one time after another, and we're adding up that sequence. Or it can simply be two groups with the exact same attributes, the same mean and the same standard deviation. Notice that we do care that these random variables are independent in both cases. That's the prerequisite that we have here. Okay, so two examples. The amount of cereal poured into a small bowl varies with a mean of 1.6 ounces and a standard deviation of ½ ounce. A large bowl holds a mean of 2.9 ounces and has a standard deviation of 0.3 ounces. You open a box of cereal and you pour a small and large bowl of cereal. If the difference follows a normal model, so to qualify, remember that means we have independence between these two bowls of cereal. One bowl of cereal, how much cereal is being poured in it is not affecting the amount of cereal going into the other bowl. What's the probability that the small bowl contains more, probably the small bowl contains more than the large bowl? So first, let's represent our two random variables. I will have x. X can represent the small bowl. And y will represent the big bowl. And we have some information here. Let's see the small bowl. We know the mean for that. We know that E of x, the expected value for the small bowl, is 1.6. We know that the standard deviation for the small bowl is 0.5. For the big bowl, the average, or E of y, is equal to 2.9. And the standard deviation of y is equal to 0.3 of an ounce. So the type of combination here is we're being asked about the difference. All right, we're subtracting them because we're trying to see if the small bowl has more or less than the large. And so here it says, when looking at the difference, what's the probability that the small bowl contains more than the large bowl? So we might write this x more than y, small greater than y. And we can subtract y from both sides to show that difference, to get both variables on the same side. X subtract y greater than 0. So that's the same statement. This is the distribution that we are interested in, the probability from and the characteristics for. On any of these problems, we would need to be able to talk about the expected value, figure out the new expected value, and figure out the new standard deviation before we can find any probabilities. So we need to look at what is expected value for x subtract y. And then, of course, what is standard deviation for x subtract y. First, let's look at x minus y for the expected. So over here we have subtraction. Notice for both of these expected values that they follow suit, right? The addition inside expected value, when you have the two different random variables, you're going to just add the averages, right? You do exactly what you see. You see plus, you do plus, or addition. Then for the subtraction, you see subtraction, you calculate the subtraction, the difference of the two means or expected values. In other words, here, this is equal to E of x subtract E of y. And the notation, by the way, on this page, the a's and b's, that's just saying if you were multiplying this variable by something. So if someone had said, hey, double the x plus 1/3 the y, you know, you're still doing a combination, but you have something being multiplied through. You would pull that multiplication out in front and multiply the average. Here we just have a 1x subtract a 1y, so that's why we just get a single E of x subtract E of y. So that looks like 1.6 subtract 2.9. That gives me negative 1.3. for my expected value. And now let's calculate our standard deviation. So for standard deviation, Let's see what we have over here. We have variance whenever we're looking at combinations that have addition or subtraction. Notice that regardless of whether you're adding or subtracting, you will always add in this formula because variance will always get larger with any type of combination. So here we will add whatever you were multiplying those random variables by, it would have been pulled out in front and squared before being multiplied. Again, we're just looking at x subtract y, so we have the subtraction part there and the addition part here. There's nothing being multiplied in front of these. So what I'm saying is that for the variance of x subtract y, that would be equal to the variance of x plus the variance of y. Now remember, all that we have here is standard deviation. So in other words, the variance is equal to, let's see, to get the variance from this first standard deviation, I'm going to have to square 0.5 and then add that to 0.3 squared. Now it is true that if we want, and we do, if we want the standard deviation rather than the variance in the end, we would say that the standard deviation of this statement is equal to the square root of the variance, which is the square root of this stuff right here, right? That's supposed to be the sign continuing, which is the same thing as the square root of this down here. But please notice that we cannot just add the standard deviations because we are not guaranteed with an addition under that square root that we will get the same thing. On some occasions we might, but on some occasions we might not. So we are not really supposed to try to cancel those squares with that square root. That's not appropriate. So let me grab a calculator for this. So we have second square root 0.5 squared plus 0.3 squared, close the square root. So we have the standard deviation for this combination is 0.583. Okay, so we have standard deviation, we have expected value, standard deviation. So let's go now to the normal calculator to find the probability. Before I go there, maybe some sketching out of what we're looking for will help though, because we are focusing on x subtract y, but we've been asked, what's the probability of this? What's the probability that x subtract y is greater than 0? So we're saying, what is the probability of x subtract y being greater than 0? What is that probability equal to? This is the big question. So let's take these features and go over to the normal calculator. So stat, calculator, normal. We said we had a mean of negative 1.3. We have a standard deviation of 583. Okay, and we want the probability of, we see an x here, but that's representing x subtract y, and we want to say greater than 0. Oh, whoops. I probably shouldn't have done that. I need to put the 0 back here and let it, here we go, compute. So I am seeing 0.012, it says 87, but I'm going to say 0.0129. So the probability is approximately we can actually say 1.3% chance that the small bowl will contain more cereal than the big bowl. Let's look at one more example. Bob works at Walmart. The mean purchase of his customers is $200 with a standard deviation of $50. If Bob checks out 100 customers, what is the probability that he has rung up more than 21,000? So here we have something repeating. We have the same characteristics. The average is $200 always. So we have the same characteristics here. Standard deviation is always $50. And we have this repeated process where a fresh customer is coming to the line for 100 times. So we have the sequence here. In other words, if X is my random variable, we have the characteristics of X. This is each time someone checks out. We have E of X is equal to 200. We have standard deviation of X is equal to 50. And as far as the formulas we're about to see, what we're doing here is we're going to say, well, there's the first customer plus the transaction with the second customer plus the transaction with the third customer, on and on and on until we get to plus the transaction with the 100th customer. So as far as the formulas go, this 100 is taking the place in the notation of the M. So M is equal to 100. Let's go back to our formulas. Down here, we have that for this sequence, the expected value for the sequence will be M, however many times it happened, times the average. Kind of makes sense, hopefully, because if you're getting $200 approximately per customer and you have 100 customers, you're going to say, oh, look, I've got about $2,000, right? You're going to keep adding 200 to your drawer or your transaction history. So that's pretty straightforward. Now we have variance and standard deviation. We can use either of these. So it's not as strict as up above with the combinations where you're always going to get variance first and then square root if you want standard deviation. Here we have a formula that's set up directly for standard deviation if we want it. So we're going to take that sigma, that's standard deviation, and multiply it by the square root of M. Okay? So our expected value for this sequence is equal to 100 times E of X, which is 100 times 200. Oh, it's 20,000. Oh, please forgive me for saying 2,000. If you all don't know, I tend to make simple mistakes like that when I'm doing math in my head. Okay, 2,000 or 20,000, not 2,000. Okay, and then we have that the standard deviation is equal to whatever the standard deviation was multiplied by the square root of n. Well, the standard deviation is 50, right? And m is still going to be 100. So we have 50 multiplied by the square root of 100. So that gives me 50 multiplied by 10. That looks like 500 to me. So I now have my standard deviation and my expected value. Now let's continue. What is the probability that he has rung up more than 21,000? So what is the probability that this sequence, the x1 plus x2, all of these customers coming through, adding up to that 100th customer, what is the probability that all of that is more than 21,000? And actually, we should put more parentheses because what we're saying here is what's the probability of that, right? Because just like a second ago, when we said, hey, when we have the x, it's representing whatever it was we were talking about. Right here, all of this in my little normal calculator, that's represented by the x. So we're looking at x greater than 21,000, since that's the combination we're interested in. Okay. Let's go back to StatCrunch then. The mean we said was 3,000. Let's see if I put that in right. Okay. And we said that the standard deviation was 500. Let's check that. Okay. And we're looking for greater than 3,000. I see 0.0228. .0228. How about I think I said? So in other words, that would be about 2.3% if you want to round just to 1 decimal. Or you could have said 2.28%. I had already rounded that 8, so normally, you don't double round. What you might have said is, okay, well, I'm going to round to 1 decimal, and so you had something like this, and then whatever was coming next, and then so of course that still rounds up to the 0.3.